Hello, everyone. I'm Nicole Shue, and I'm a National Research Council postdoctoral scholar at the U.S. Naval Research Laboratory, which basically means that I get to work on interesting research problems to build underwater vehicles with potential applications for the Navy. Today, I'm here to talk about resonance in nature and bioinspired squid robots. I'll go into what the definition of resonance is, how animals exhibit resonance, how we as scientists and engineers can design robots that mimic these resonant animals, and how this all fits into the world of controls. But first, let me motivate this more broadly, because you might be wondering, why make squid robots? Well, as a preview of this talk, bioinspired swimming robots are an additional tool that we can use for ocean exploration. And this is a graphic where you can see more traditional underwater vehicles on the left and these bioinspired robots on the right, some of which leverage resonance. So to pull back a bit more, there is so much that we don't know about the ocean. In fact, over 80% of our ocean is still unmapped, unobserved, and unexplored, even though we know that the ocean is crucial for regulating the climate, modulating oxygen and carbon dioxide levels, and providing us with food, medicine, and transportation. So it's important to monitor the ocean to track changes in temperature, acidity, and concentrations of nutrients as climate change affects our waters. We want to be able to detect and prevent situations like coral bleaching, shown here in the contrast of healthy versus bleached corals in the top photos, and harmful algal blooms like this image of Lake Erie. And of course, for the sake of scientific curiosity, discover new animals like this not so new but oh so cute sea bunny called a nudibranch. The current tools we have for monitoring the ocean include remotely operated vehicles, or ROVs, which are kind of like small cars that are attached via these long cables to boats, and autonomous underwater vehicles, or AUVs. These have great advantages and can travel fast speeds over long distances for data collection, such as mapping the ocean floor or deep sea exploration to uncover new animal species and behaviors. But many of these technologies are still limited, and the disadvantages include being costly, bulky, consuming high power, and leaving larger vehicle wakes that might disturb more sensitive areas of the ocean, like more delicate animals. This video shows some of the surface perturbations from boats and skiers as a more visual representation of wakes. So to expand our capabilities to monitor the ocean, I've listed some of the needs, and this is not a comprehensive list, but we want to work towards more low power and low cost solutions that minimize environmental disturbances to aquatic life. To achieve this, we can use a combination of math, science, engineering, tech, and biology. This is where we can look to nature for inspiration because we can build bioinspired aquatic vehicles that can leave more natural wakes to reduce these environmental disturbances and take advantage of the tools that biology has already designed for us. For example, one bottleneck of robotics is that it's very difficult to match the energy efficiency of real animals. Generally, robots are less efficient than their animal counterparts or can't match certain capabilities like turning speed and agility. So looking towards animals, we can pick a model organism depending on the traits we most desire. For example, fish and manta rays are fast and agile, but if we want something that's energy efficient, then jellyfish or other squishy animals like squids are the way to go. And speaking of nature, if you can hear any birds chirping in the background or cicadas, that's because it is cicada season once every 17 years, and so the birds are having a feast outside right now. But part of the reason for choosing soft and squishy animals is that these animals can store elastic energy in their elastic, stretchy tissues, and so they can also take advantage of the concept of resonance. So let's start off with a textbook definition of resonance. Specifically, mechanical resonance is defined as when a vibration of large amplitude occurs when the system is driven at a frequency that is at or near its natural frequency. Okay, so what does this mean? Well, each system has a natural frequency, and if an external force that matches this frequency is applied, then the system will move more. This is just another way of saying, under specific circumstances, you get more bang for your buck. One classic example of resonance is in music. Stringed instruments like this guitar played by Taylor Swift makes music because their strings vibrate at certain frequencies and harmonics. You might have heard these terms before in a music class, for example. So stringed instruments can resonate at frequencies that match their fundamental or overtone frequencies, and this image shows a tuning fork that can be used to tune a guitar. Now, if we want to explore what acoustic resonance is, which is a form of mechanical resonance that we can hear, let's see what happens when we have two tuning forks. As shown in this demo, as it plays in the background, both tuning forks are pitched at 440 hertz. So when they're hit, they should make a noise that is 440 hertz in frequency. Notice that when one tuning fork, the one on the right, is hit, the other one, the first one, also makes a noise. And the microphone is there so that we can amplify the noise and make it more obvious for us as listeners. So I'm going to stop talking and you can kind of hear what's going on. So going back to the definition of both mechanical resonance and acoustic resonance, you can see that there is a vibration that occurs in the first fork after the second one is hit. And this does not happen when the second tuning fork is altered so that it no longer gives a frequency of 440 hertz. So as you can see, this only happens at or near the natural frequency of the first fork. But another way that I like to think about the concept of resonance is just with the everyday use of the word. That person, that song, that thing that resonates with me. Or we're on the same wavelength. I mean, you've heard these phrases before. So this is a picture of me with some of my friends, before the pandemic, of course. And you just have people you resonate with. Like when we asked the waitress to take a photo of us and without discussing it, we just did this very weird, unnatural handshake pose that we've never done before. But silly anecdotes aside, the point is you already understand the concept of resonance just because of how we talk about resonance, wavelength, and vibrations in day-to-day life. And really, I just like all of this terminology because ultimately it reminds me of physics. We're talking about frequency and wavelength, and if you don't know, you'll learn this in the next few years, but these are related concepts because the speed of light, c, is equal to the wavelength times frequency. And this equation is completely unrelated to the rest of the talk, but I mention it because I personally like when talks have tangents, and that's something that really resonates with me. But it also brings me to my next point. What even is frequency? Well, frequency is the inverse of time, and you can kind of think of it as a rate. So here, as an example, heart rate is usually measured in beats per minute, BPM. This is a cartoon of a regular heart rate, which shows some kind of amplitude over time. And I think it's important to note that we can represent the same data in multiple ways, either in the frequency domain, which is usually what we think of when we talk about heart rate and other frequencies. So in this example, let's say it's 60 beats per minute. Or we can look at this data in the time domain, which is this graph, and then we can say that 60 beats per minute is the same thing as saying there is 1 second in between beats. So same information, different presentation. So getting back to resonance, we can also observe resonance in nature. This is a jellyfish called the hydromedusa, which exhibits mechanical resonance. Naturally, these jellyfish swim near their resonant bell frequency, which then causes a 40% increase in their amplitude and a substantial reduction in their energetic cost. One metric of energy efficiency is the cost of transport, or COT. This is defined as the energy per mass per distance traveled, and you can think of it as the inverse of miles per gallon, so something like gallons per mile. And a low cost of transport therefore relates to a high energy efficiency, which is good. And this cartoon plot shows the cost of transport for a variety of different representative animals. And as you can see, jellyfish have the lowest cost of transport compared to these other animals, so we might learn how to make more energy efficient robots by studying jellyfish. And to relate this to frequency, for jellyfish and squids, we can look at their swimming pulses. The typical unit that we use for frequency is hertz, which is 1/seconds. For some background, here's a jellyfish shown upside down. And this is an image of the jellyfish placed on a dish with the underside facing you. You can see that its muscle structure is shown here in red, a single layer on the underside. And if this jellyfish pulses twice every second, then its swimming frequency would be 2 hertz. We can see a visual representation of that. So on the left is another jellyfish bell on the dish. Again, we're looking at the underside of it, and I've injected these red tags into the bell. If you pay attention to one of these tags, like the one in this blue circle, you can see that every time the jellyfish pulses, the red tag moves a little bit. So from videos like this, we can then track that red dot to get a tag displacement over time. This is the time domain plot. But again, we can represent the data in different ways. And so we can look at this data both in the time domain here, as well as the frequency domain. So that's in that those units of hertz. And you don't need to look at the plots too much, just know that on the left is the time domain graph, and on the right is the frequency domain graph, and both again are giving the same information just in two different ways. So now we have a better idea of frequency, jellyfish muscles, and how this relates to swimming, we can go back to that concept of resonance. So jellyfish aren't just resonant in their pulse rate. Remember that every system has a natural frequency, and the jellyfish's natural frequency not only affects their pulse rate, but also the speed of their muscle wave, that red ring of muscle on their underside that I showed earlier. So this video shows a computational jellyfish turning, with the muscle activating from one side first to cause this animal to turn. And you can see the fluid moving around underneath the jellyfish bell during this turn. But jellyfish aren't the only squishy sea creatures. Of course, this talk title includes squid robots. So this is an image of an adorable Hawaiian bobtail squid, which is a similar type of animal tissue, very elastic and squishy mantle or squid head that can store elastic energy. And the advantage of looking at squids over jellyfish is that squids can swim very fast, up to 8 meters per second, in addition to things like maneuverability and complexity. Researchers in the UK took this idea of squids and jellyfish and created a squid-like robot that uses resonance to swim. They took this idea of a squid, shown here on the left, and simplified it down using math, geometry, and physics. This is a representation of the squid robot, and in particular, this series of two circles with this squiggly line in the middle is the physical abstraction of this squid or squid robot into a mass spring mass oscillator with a spring constant K. Now, what does this mean? Well, these relate back to some of the equations that you saw earlier in Danny's talk about resonance, and that's really all this is saying, that you can simplify a biological or a robotic structure into a series of masses and springs. And using this bio-inspired robotic design, the squid robot is shown here swimming upwards. You might even say that it started from the bottom, now it's here. Probably not cool to use Drake memes anymore, but whatever. So from collecting data over many experiments, the researchers created these plots. The x-axes, those are the horizontal axes, for all three are the frequency that they tested over the robot's natural frequency. So we want to see more happening when we're approaching 1, because this is where resonance should kick in. And with some margin of error, that's exactly what happens. So here you can see that speeds increase on the top left plot. The top right plot shows efficiency also increasing. And on the bottom is the cost of transport. And remember that we want low cost of transport because low COTs result in high energy efficiencies. And that's exactly what we're seeing. In fact, the cost of transport of this Squid-inspired robot matches the cost of transport of natural jellyfish, which is exactly what we want to do. And so now we're able to build a robot that matches the energy efficiency of jellyfish, the most energy efficient animal. That makes us one step closer to using these bio-inspired swimming robots for ocean monitoring. And now I want to mention a different approach to bio-inspired design, which is a field called biohybrid robotics. This involves using both robotic components and live animal components, and we can potentially use whole animals with a swim controller embedded for ocean exploration. The image on the left is a real jellyfish with a swim controller embedded. That's this blue device here in the center of the animal. On the right are cartoon schematics where the components are labeled, but the idea is that the microelectronics can attach into the live animal and control where the jellyfish swims. So instead of mechanical actuators, which you were introduced to earlier, we're using the animal's own muscles as biological actuators. and this does not hurt the jellyfish. And if you're curious, I can talk more about this in the questions, or you can read my ethics paper, which is here. By using this system, I've demonstrated that we can increase jellyfish swimming speeds up to 3 times what it would normally do, at only a 2 times increase in the cost of transport, which shows the potential for both faster and more energy efficient jellyfish swimming. So this is a video from the lab of the jellyfish swimming in a tank against a background current. You can see the flow of the water, as opposed to the other normal jellyfish that are just kind of floating around being carried by that current. And this is a video of this bionic jellyfish, that's that biohybrid jellyfish, swimming in the coastal waters of Woods Hole, Massachusetts. So you can see that the jellyfish still is able to swim in real ocean environments. So to conclude, bioinspired robots can take advantage of things that animals already do well, like resonance and energy efficiency. We can learn from nature to improve engineered designs and really create the best of both worlds, both the natural world and the artificial world. Bringing this back to controls, all the videos I've shown so far are when robots are being controlled in an open loop. This means that the robots don't have any sensors that feed back into the system, so the robots are just being told to swim at certain frequencies without any other information from the outside world being communicated to it. The next step would be to include closed loop feedback, such as by adding sensors, and I've included an example of a few sensors that we can use. So we can include things like temperature, acidity, salinity, etc., both so that we can improve the controls aspect and also so that we can have practical applications with these robots. So by incorporating sensors, we might be able to send out these squid and jellyfish robots into the ocean to collect real data and track climate change. And the last point I want to make is science and engineering encompasses a huge variety of disparate topics, as you've already seen in today's talks or will see later on today. Personally, I find the most interesting problems are at the interface of biology, robotics, and physics, but there is so much out there and so many topics that can really seem foreign at first, but I guarantee you that you are already familiar with a lot of these core concepts. So I hope that I've convinced you the merit of using aquatic animals as inspiration for squishy, soft underwater robots. And with that, I'd like to thank you all for your time and for listening to me. And I can answer any questions, or please feel free to email me. My email is listed at the bottom of every slide. Thank you very much.